Hi, I'm Maciej, and this video is one part in a series explaining my idea to use Mathematica for formal methods. In this part I will continue my exploration on how different types can be modeled and represented internally. So, as you have already seen, the idea is to have a system with a set of packages, and in each package we can expect to be able to define types, objects and operations on them. We have already seen several useful what are the useful type classes that can be modeled in the system, and in the previous video I have shown how numeric types can be described. Now I will focus on array types. So just as in previous parts, I will start with a fresh Mathematica session with some code already typed in so that I can use it immediately. I'm loading the FMT package. Now I'm creating the new system. This system is empty, it doesn't contain any definitions. But I will declare package A and define two simple data types that are similar to the types I have shown in previous parts. So we have a type color, which is a numeration, and my natural, which is a numeric type based on the built-in integer type, and with some invariant that the values of this type are expected to be at least 0. We can have a peek in the internal structure. Again, this is not necessary, but to explain the idea of FMT, it's good to see how it evolves. So we have our definitions of types with the definitions are sufficiently different that they will allow the system later on to figure out how they should be processed. So what I will do right now is I will define some array types. So we have define data types in package A. Oops. Okay, and as in previous cases, it's possible to define multiple types at the same time. Let's have an array of colors. So that should be enough. There is no need to provide any more information. Colors is a name of the array type, which has size 10, and the element type of this array is the enumeration type color. I can also have some other array type. Let's say that I will refer to my natural type. I can make it a bit smaller. I have my new definitions. We can have a peek to see that the representation was extended, and all these definitions are indeed represented in the internal data structure. And it should be also possible, since the array can have any other already defined type as the element type, it should be also possible to define the array of arrays. So that should be a way to represent multi-dimensional arrays. Some programming languages distinguish between array of arrays and truly multi-dimensional arrays, but I think that such a distinction has no big added value, and it's difficult to represent it in a generated C or C++ code. So we will not focus on it. Here what I wanted to do is I wanted to have an array of arrays. I have values as the array type already defined, and now I'm defining another array with 4 values, with 4 arrays inside. Okay, so this is a simple way to have multi-dimensional arrays. And again, I can see my new definition being added to the internal data structure. Of course, what I can do with all these definitions is I cannot create objects, I cannot define operations. This I will handle in future videos, but I can already show that the code can be generated for this package. Okay, so this is a C++ definition with the types that I defined and with array definitions as well. What is important here is that different programming languages can have a different opinion on what is the right starting index for the array. For example, C and C++ programmers they are used to treat 0 as the starting index, whereas Ada programmers prefer 1. And of course, everybody is ready to have heated discussions on which is better. I didn't want to take any decision on this subject, and the way this can be solved with Mathematica and with FMT is by means of some internal property that the code generator will understand. So as you can see, because the starting index has no impact on how types are defined, except not in C and C++, but in Ada it will make a difference. Here you can see that the default starting index 0 is used in type definitions. Okay, and what I can do is I can set the option for my system. Okay, so this setting is system-wide. It affects all packages and all definitions. What I will do here is I will set array index offset to the value 1, which is what Ada programmers would prefer. Now, when I generate the Ada code again, I will see that my array definition has changed. Of course, it will be a bit challenging later on to properly take it into account when generating code for actual expressions and for array accesses. But this is something that can be done, and this kind of treatment can be a good solution that can be accepted by programmers both from the C and C++ side and the Ada one. Okay, so in the next video I will show how structures and records can be defined and represented internally. And for the arrays, thank you very much. Thank you for watching.